I hope you all can hear me clearly and see my screen. Thank you, Anamitra. Thank you, Sahil. Let's start with the work. A very good morning to all of you. Last few lectures, we are discussing about image restoration. In the last two classes, we spoke of how the noise comes in the system. And in the last class, we did talk about noise estimation. Sorry, we did talk about noise models. What are the various noise models which are available as of now? In today's class, we will talk about how, if an image is given, you can find the noise parameters. So, I'm going to introduce the theoretical part in brief, and towards the end, we will check it by a small experimentation. So, going ahead, today's class we will talk about histograms of noisy images, and we will learn how to estimate noise parameters. So to begin with, how to estimate, how to find, or how do we know how does the histogram of a noisy image look like? Now here is my test or the sample image. You can see that the sample image or the test image is a very straightforward image. So remember earlier we took the test image of those circles. Generally strategy is straightforward. You can see now that for testing we use little simpler images, learn our fundamentals, our basics on that, and then extend it to the more complicated and challenging images. So that is the whole idea. Now here I have a simplistic image. You can see that this image has three regions. There is a central white region, then there is a in the middle there is a light gray region, and then the peripheral dark gray region. So any pixel in this image belong to any of the three intensity values. Either it is white, or it is light gray, or it is dark gray. There are no other intensity value assigned to these pixels apart from these three. So how would the histogram look like? So a histogram, if you take the histogram of this, then the histogram would look like three peaks. Remember, in the histogram we always go from the dark here, 0 here, to the brightest portion, 255 here. So from 0 to 255 if we go, then there are three distinct peaks. So these three distinct peaks can represent these three regions. So ideally, if it is all white, all light gray and all dark gray, then these three peaks are three lines. The height of the line shows or reflects number of the pixels in each of these regions. So this region has these many, this region has these many number of pixels, this one has these pixels, and the brightest one has center pixels. So this is how the histogram of a normal image look like. This image does not have a noise. Now what I'm going to do is going to add some noise to it. So if I'm going to add some noise to it, how would it look like? So here is my example. I have added some Gaussian noise to it. So you can see that whenever the Gaussian noise comes in, the Gaussian noise bell curve will appear. Now you no longer get those peaks, sharply defined peaks. Instead, what you are getting is or are the bell curves around those peaks. So this bell curve which you have obtained is around these gray pixels. So depending upon how much noise you add, the noise will be added about this mean value. Remember, there are two parameters in most of the noise characteristics, mean and standard deviation sigma, or sigma square sometimes, which is called variance. So the mean and variance are the two important parameters. So look at this carefully. This bell curve is distributed about this mean. That means the noise which is added to the darkest region has the mean at the darkest region. So the mean is this point only. About this, taking this point as mean, the noise has been added. So noise has been added according to this as the mean. So that's how it will happen. Again, in this case, you will get about this mean, you will get some more noise here. Again, in this case, about this as the mean, you will get the noise here. How much will be the width of the curve? So remember, the width of the curve is represented by the amount of standard deviation, sigma or sigma square, which is called variance. So that will decide. If your variance is large, then you will get large width, and then if the width is very large, then these can overlap as well. So do remember that. You can also see that this shows a bit of a green here and a red here. I leave this question to you, that why is it showing it that way? But yeah, before we conclude that, this is how the transformation occur. If the image is noise free, you get, then in the flat regions, when I say flat regions means the regions of uniform intensity, you get a straight peak, sharply defined line as your histogram. This is a region of flat intensity, you get one line. This is another region of flat uniform intensity, you get second line. This is the third region of flat uniform intensity, you get the third line. So you get these three lines for the flat regions. Moment the noise is there, those lines no longer are lines. So in this region, if it's noise free, I'm expected to get a line. But if it's a noise, I get a bell curve. So by knowing the histogram of this region, I can figure out that how much noise is there. So we'll come to that towards a little later. This is how the noise image of different types look like. The left hand side, if I add a Rayleigh noise in the image, then you can see that instead of getting a perfect bell curve, my histogram of the image corrupted by relay noise will have a skewed curve here. So this side it is different than this side, and this side shows a cutoff here. So that is another example of relay noise. So relay noise comes in the picture over here. If that becomes too skewed, then it is Erlang noise, as we had discussed in the last class. So you look at these parameter or look at these shapes, and from these shapes you can judge what kind of noise it is. Remember, if it is if the bell curve is symmetrical for a flat region, then it is what is called Gaussian noise. If it is asymmetrical, then it is Rayleigh, and it is as skewed as this, where this one end almost is vertical, then it is Erlang. There are other types of noises also. So this is exponential noise. Look at it, what is happening. In the exponential noise, you get the noise only on one side of the your mean. So if had there been no noise in the image, you would have got a sharp line on this edge. Noise, exponential noise is added only onto the one side of that average value. So this is the exponential noise. So whenever it is present, the bell curve becomes, the curve becomes half. There's nothing on this side falling, only curve is on this side. So this is how the exponential noise is represented. A uniform noise, so if you take this section, so this section has a uniform spectrum now from some lower value to some higher value. This section, if you come to the gray section, then gray section again has a similar feature, but not at the extreme end, but in the middle end. So instead of what was a line in the middle end is now spread out a bit. It is now spread out so much here. And what was the dark gray, again that has spread out a bit. Now remember, the width, larger the width of the uniform noise, then more will be the width of these towers, and eventually they merge into each other, and in that case it is difficult to identify, so be careful. So that is how the histogram would look like. How would the histogram of a salt and pepper noise or an image corrupted by salt and pepper noise look like? So that is again very straightforward. By definition, salt and pepper noise has some probability in the white region and some probability in the black region. So it creates some pixels which are perfectly white and some pixels which are perfectly black. So in salt and pepper noise histogram, you will get a line at the extreme end which represents your salt noise, the right end of the histogram, and you get a line at the left end of the histogram which represents the black part or the dark part. Rest of the, here you can see that the black or the pepper noise or the black part, which is also called pepper noise, is large, so it is more scattered in this image than the salt noise, which is completely white. The rest of the histograms will not be affected because the salt and pepper noise don't fall into those categories. Another third kind of noise by observation is periodic noise. So if you look at a periodic noise, it may look like this. So you have a constant period. This is a noise on which a sine wave or noise which has a parameters of sine wave has been imposed. Periodic noise, you should look at it and you should be able to identify. You can see that this is changing uniformly. So this is the periodic noise. If you have periodic noise, by observation, then the best strategy is not to get the histogram but to get the Fourier transform. So if you get the Fourier transform of this, then you can see there's two dots here. One dot is here, another dot is here. These are the two dots which represent the presence of this sine wave in the Fourier transform. So that is how you identify the pinpoint location of a periodic noise in the Fourier transform of the image. So how do you estimate the noise parameters? The noise parameters can be estimated in various ways. One is from the sensor specifications. So whatever make of sensor is there, if you if you speak to the manufacturer or if you look at their guidelines or data sheets, then you will do provide us with the some sort of estimate of the noise. So that becomes very handy. However, that is not always available to the end user. Just to give you an example, um, one of the largest manufacturer of sensors, CCD, CMOS sensors is Sony Corporation. Most of the mobile cameras, when they implement or employ their cameras, they buy the sensors from Sony. So whenever the Sony Corporation works, it does creates data sheets, test sheets, amount of noise, response to light, etc., etc., and then give it to these mobile companies. But the mobile companies go ahead and further use that data to make the images which are as good as possible and then give it to you. So what you will be landing up at the end is not a product from Sony, but a product from, say, the mobile company. So sensor specifications are generally not known to the end user unless and until you dig deeper. But yes, that's one of the sure shot ways to figure out what would be or how much would be the noise. But there's a handy way to figure out the noise as I have already described. You sample out a small patch of uniform intensity from the noise, from the image. Once you do that, you can figure out its probability distribution function, histogram that is. You have already written code to find histogram in your image analysis lab. So you can use that to find out the histogram. Once you find the histogram, then you can, using that histogram, that is histogram probability distribution function, you can calculate your z bar, that is mean, and you can calculate your variance, that is sigma square, and hence root of it as a standard deviation. So both the parameters can be calculated and therefore can be further processed. So in this class, I would like to stop here as far as theory part. In this class, I would like to stop here as far as theory part is concerned. Let me demonstrate a small experimental part to what we spoke of today to finish this lecture. So here I have an image. Already I have created it. I hope you all can see it. Unfortunately, it is not very big image. It is 156 cross 260. So small image. Now let us take its histogram. and see how does it look like. I'm using image or Fiji, whatever you call it, for this kind of quick experimentation. The Fiji does give us a very quick experimentation. So this is how the histogram of the total image look like. Now what I can do is I can process the image and add some noise. So I will add a noise which has a standard deviation of say 50. Will add Gaussian noise of standard deviation 50. What it means is, suppose wherever a particular color pixel is there, suppose this is a gray here, it will take this and to that pixel randomly it will add a noise of standard deviation of 50. So I will say OK, and you can see that the noise has got into the image. Now I can figure out the histogram and we will try to see how the histogram differs. So these are my two histograms. You can easily see. My left hand side histogram is the histogram of the original image. You can see that of course this is a normal image, it's not a grayscale image. Since it's a normal image, you will not get straight lines, you will get some parameters. But you can see that centered around that, the largely the noise has been added, and the noise becomes it, it broadens, converts this into a bell curve. This bell curve existence actually shows that you have a noise, a Gaussian noise here. Okay, so now I will take a screenshot and keep it aside, and then I will go back to my original image. Okay, originally it was a colored image, so we need a 8-bit grayscale. So this is the image now. Now what we can do is, let us do some sampling. As I said, you take a patch which is of uniform intensity. So let us find out a small part which has a rather uniform intensity, difficult to find except in these two regions. So one is this head region which is black, and one is this which is slightly gray. So I'm going to take a small part of this. So I will make a square selection here and use this tool to create a small part. Okay, and now I go to analyze and I go to histogram and I click on live. So it gives me the histogram only for this part. Okay, now the beauty is this, that if I shift it, my histogram will change. Can you see? It has slight variation. I can shift this entire thing at some different place also. Let me select a small patch here, and you can see that there are some variation. This is more uniform, so I will stick to this small portion, And now we will keep this at one place, and as usual we will add our noise to it. So we will add noise with this selection. We will go to process, noise, add specified noise, take 50, add it once again. And now if you have a noisy image, then you know that this part of the image should have had a uniform noise. Now I can select a little portion over there, and you can see the difference in the histogram. The histogram has a lot of spread out. Just that I think we are selecting a too small a section to figure it out. So let me do it quickly once again. I will assume this entire section as a uniform section, so bigger section, and see what do we get. This is the image that you will get at one place. Now process, add some specified noise. I would rather add a little lesser noise, 25. And again I will select this section, little larger section, and then send it to analyze histogram, and you can see the spread. So, and thankfully the softwares gives the standard deviation calculations quickly. So if you have the same section, then you can see that this is without noise, mean is 89 and standard deviation is 13. You can see in the same section your mean is almost the same, 91, but standard deviation has increased to 28. So from 13 you have gone 28. Here the spread was little, here the spread is much more. So this demonstrates the presence of Gaussian noise. You can see that what was a straight peak here has now a symmetrical bell curve. Unfortunately, this image does not have large patches which would have uniform intensity. So for example, in a typical image, generally we choose a region of sky where the intensity in patches is assumed to be uniform. Also, if you take the image of larger dimensions, this is 156 by 260 pixel entire image. So what I am selecting is hardly um, total here around 200 pixels, 200 or 260. If you select a larger pixel, larger image, larger patch, you get much better results here. So with this, we can stop this lecture. Next class, we are going to look at the techniques that we can develop to eliminate these noises. Thank you.